Hi guys, chapter 23, all about electric current. Electric current is a little abstract if you think about it. A lot of people think that electricity is those electrons zipping down the line. But if you think about it, you flip a light switch at home. It's not like Duke Power's sending out electrons from the power plant zipping all the way to your house. That's not how it works. As we learned in the previous chapter, every charged particle is surrounded by an electric field, right? That force field around them, all right? But what happens is when you turn on a switch, that connects the circuit up, right? A complete circuit allowing energy to flow. Well, this energy flows through these electric fields, all right? Because electrons, if you think about it, they're all negatively charged, right? So they repulse each other. Right, so that means they all want to push apart, okay? But we've got to get them all going one way to get the energy to your house, right? So this electric field, by closing the circuit, these electric fields nudge. They like nudge and excite each other and send this nudge on down the line. So it's like one electric field nudging the next one, nudging the next one, and that gives the direction. So the energy flows at the speed of light through all these electric field nudges. Right? Now the electrons do move some, and you do have them moving down the line, but that's not what carries the energy. It's this domino effect of electric fields that carries the energy. So the electric fields move at the speed of light, not the electrons, and that is how you get your energy to your home. Okay? And here's a little simple diagram of electricity to show the flow of electrons. Right now, electrons do move, right? And it's a lot simpler to think of electrons moving and carrying that electricity, that electric energy to you, but it's really that electric field, right? But a lot of times we'll just refer to it as just the flow, right? I like to refer to it as the flow of energy because that's what it is. But you'll always see some images like this. Alright, moving on. So charge flow, energy flow. Okay, now we've discussed in previous chapters with how to make fluid flow, right? You gotta have a pressure difference to make any fluid flow. How do you make heat flow? Well, you gotta have a temperature difference. Well, guess what? It's no different here. To get electric energy to flow, you've got to have a difference in that electric potential, right? Now, if you recall, electric potential is the electric potential energy per charge, right? Now, if there's no difference in that, no flow, right? So if you look at this diagram, right, we've got a positive charge over here, so maybe this is a 6-volt battery. I don't know. We're just going to say it is. So we've got a positive 6 volts over here, but then you've got 0 volts over here, right? So there's a difference between the two ends of this battery, and that gets you the flow, all right? Now this flow always flows from high potential to low potential, just like anything else, right? Fluid moves from high pressure to low pressure. Heat moves from high temp to low temp. Same thing here, high voltage or potential to low potential, all right? Well, this flow is called your electric current, all right? It's your electric current, just like current in a river, air current, anything. It's movement in a direction, all right? So to have this continuous current or this continuous flow, we've got to have a battery or a generator or some kind of source, energy source to keep this maintained, right? To keep this flow pumping, right? That is how you continuously keep the flow going without running out. All right. Well, this flow is called your electric current, right? Your electric current. Okay. So that means how much charge is flowing by a particular point at any given time, right? So you can see from our equation here, current is charge over time, right? Now there are other ways to measure current, and we will get to that. But here's the basic definition. How much charge flows per time. All right? Now we measure current in amperes, all right, abbreviated by an amp, or sometimes you'll see it just an A. and that is charge, which is measured in coulombs, over time, which is in seconds. So a coulomb over second gives you an amp. All right, there's a little video for you right there to help you with that. So these sources, right? We got to have this energy source, right? So we got batteries, all different kinds of batteries. Generators, either mechanical, crank it up yourself generator, or here's a generator that runs on gasoline engine converting that over. All right. Well, what all these voltage sources are doing is converting energy, whether it's chemical energy in the batteries getting converted over, or mechanical energy in the generators getting converted over. That's all energy conversion, right? Well, it takes work to do that, right? It takes chemical breakdown, chemical reactions doing work to pull some ions apart in the battery to give you a positive and a negative side of the battery, the high and the low potential. Same thing with the generator, right? You have to put some work in that crank to get you some energy, right? This conversion of energy is what gives us our voltage and is our pumping mechanism for keeping that current flow going. All right. Now there's resistance in everything. Just like we learned in past chapters, there's friction in everything, right? It wouldn't be reality if there wasn't. Okay? So electrical resistance is like our friction in these electrical chapters we're going to be talking about. Okay? Well, it depends on a few things. All right? But resistance is in everything. It's in the battery or the generator, in the wires, in the device you're trying to power, like the light bulbs. It's in all of that. Okay, well, how do we measure it? What does it depend on? Well, it depends on a few things. But I want to point out first this picture here to the side. These little devices are actual resistors that you can put into a circuit. Now, why would you want to put resistance in a circuit on purpose? Well, resistors help to regulate and control the flow of current, right? So if you need the current to be reduced a little bit, well, you stick a resistor in there, and it slows that flow down just a little bit. So it's a little control device, all right? But if you look down here at our numbers 1 through 4, there's the factors that resistance depend on. All right, so resistance is inversely proportional to the cross-sectional area. All right, inverse, remember, acts oppositely. Bigger area, little device. So think about this. Rush hour, right? 5 o'clock, everybody's getting off work. Do you want to be on a 2-lane back road, or do you want to be on a 6-lane interstate? Right? More flow through that 6-lane interstate, right? Bigger space, bigger area, less resistance. You get more flow through there. Resistance is directly proportional to the length, right? The longer wire it has to go through, the more resistance that can build up. It depends on the material, right? Which that's kind of obvious. If you have a conductor, it's going to flow smoothly. If you have an insulator, maybe not so smoothly. And there is a temperature dependence on there. The higher the temperature, the more resistance you get. Because think, what did we learn about kinetic theory, right? As things get hotter, those molecules, electrons, everything, they start moving faster. More collisions. That's just like you just had a 6-car pileup on the highway, right? That's really going to slow you down, right? Higher temperatures, higher resistance. All right, here's Ohm's law. Ohm's law governs everything with simple circuits we're going to be dealing with. All right, Ohm's law gives a relationship between the current, the resistance, and the voltage. And here you can see it. Current is equal to the voltage divided by the resistance. All right, or I equals V over R. All right. Excuse me. In this relationship, voltage and current are directly proportional. Get a bigger battery, increase the voltage, you can jack up how much current you have. All right, you get a bigger light bulb, so you have bigger resistance. Well, that's going to decrease the amount of current you have. All right. So here in this figure to the left, you can see different ways to rearrange that equation depending on what you need to solve for. And I like this little picture right here. All right, you can see the amp, right? That's the current trying to flow through there. Here's the voltage, which is our pump trying to push it along. But the ohm, that's our resistance. Resistance is measured in ohms for Ohm's law. All right, and you can see he's cinching down They're not wanting to let that current go through, right? That's what resistance does. Doesn't let it go through, doesn't let it flow. It kind of chokes it up, alright? So you got a couple of videos there, some extra credit on Ohm's law to get you going. Well, we've got two types of current flow, direct and alternating current. Direct current goes in one direction. Alternating current does just like this picture says, and it fluctuates about excuse me, a fixed position. All of our homes and businesses here in North America run on AC current. And there's a couple of videos there to help you understand that a little bit better. Now, if our homes use AC current, what uses DC? Well, most of your smaller electronics, laptops, tablets, etc. Well, how this works, because have you ever noticed on your charger cords for these devices, you have that big box, or your cell phone's got that big connector that you plug the USB in and plug it into the wall? Well, that big box has a diode in it, which is a converter. Converts your AC that comes out of the wall jack to DC that can be used in your device. Alright, electric power, right? Well, we know power is how much work is done over time, or how much energy gets converted per time, right? Well, that still holds true for electricity. That's the same thing. That's the definition, alright? But I worked through the substitutions here, alright, so you can see how power relates to voltage, current, resistance, all that good stuff, okay? So we know voltage is that electric potential energy over the charge, right? So energy is equal to voltage times charge if we rearrange that, right? Well, recall current is charge over time. So if we take these two ideas, put them in our power equation, right? Power is energy over time, right? Put in V, voltage, charge for energy, right? Still over time, right? Well, look at this. Q over T, well, that looks a lot like that, right? So that's voltage times the current, electric power. There you go. Circuits, right? We've talked a lot about circuits. You've even got a PDF on Moodle to tell you all about circuits, right? There's two different kinds, series and parallel. And we will talk about those in detail in just a second. Alright, but as long as you have a complete circuit, no gaps, no openings, you're going to have current flow. So series circuits, connected all in the line, only one way for the current to go. Alright, total resistance, you just add them all up. The voltage from the battery drops over each of these devices, and these drops add up to the voltage of the battery. Alright? Now, parallel circuits are different. They look kind of like a ladder, as you can see here. So you got different branches. So look at this. We've got 3 different ways that that current can run. Alright? So if we need a certain amount of current to run these light bulbs, then that means this battery's got to pump out 3 times the current of what the series circuit did, right? So that means that battery's working harder, right? But it's the same voltage across each device because of the way it's connected, but the currents divide. So the 3 currents in each branch here, each rung of this ladder, add up to the current out of the battery. Okay? You can still use Ohm's law for every one of these circuits. Okay? Now, parallel circuits are neat because the resistance in any one of these branches is less than the total resistance of the circuit. That's why parallel circuits are used in your home, because it reduces the resistance, which reduces friction, which reduces heat, doesn't cause your house to catch on fire. Alright, safety first, right? We know all about safety. So here's how all the safety works in your home. Circuit breakers, fuse boxes. Alright, you can read up about that, learn how circuit breakers work. Very interesting stuff, keeps us safe. Alright, please do all the videos, check out those extra credit questions, read your chapter, and as always, if you have any questions, contact me.